नमस्कार दोस्तों, हमारे YouTube चैनल में एक बार फिर से आप सभी का स्वागत है। आज हम करने वाले हैं एग्जाम्पल्स ऑन मोनोटोनिक सीक्वेंसेस। तो लास्ट लेक्चर के अंदर हमने कुछ रिजल्ट्स किए थे कि नेसेसरी एंड सफिशिएंट कंडीशन फॉर एनी सीक्वेंस टू बी मोनोटोनिक इज दैट टू बी कन्वर्जेंट इज दैट इट इज बाउंडेड। ओके, कोई भी मोनोटोनिक सीक्वेंस, एनी मोनोटोनिक सीक्वेंस इज convergent then it is bounded, and if a monotonic sequence is bounded then it is convergent. Okay, so necessary and sufficient condition we have proved in the last class. Also we have proved that if sequence is monotonically increasing sequence and it is bounded above, then sequence converges to supremum, and if sequence is monotonically decreasing sequence which is bounded below, then sequence converges to its infimum. Also, if we have any sequence which is monotonically increasing sequence which is not bounded above, then it diverges to plus infinity, and if we have a sequence which is monotonically decreasing sequence which is not bounded below, then it diverges to minus infinity. So these some results we have done in our earlier lecture. Today we are going to prove some important examples to establish the theorem. So first example, so that a sequence Sn where Sn equal to 1 upon n plus 1 plus 1 upon n plus 2 plus and so on 1 upon n plus n is convergent. We have to prove this sequence convergent. So first I will try to find that either sequence Sn is monotonic or not, and if it is monotonic sequence then we will see that it is increasing or decreasing, and then accordingly we will establish this example. So solution: Sn plus 1 equal to what? 1 upon n plus 1, 1 upon n plus 2 up to 1 upon 2n plus last term will be what? N is replaced by n plus 1. So if we replace n by n plus 1, then n plus 1, so last term will be 1 upon n plus 1 plus n plus 1, that is 2n plus 2. Okay, if I put here n plus 1 in place of n, then n plus 1 plus n plus 1, I get 2n plus 2, and term before this term will be 1 upon 2n plus 1, 2n plus 1, and then 1 upon 2n, and so on. So this is Sn plus 1. Also Sn is this. If I find Sn plus 1 minus Sn, then what we get? Sn plus 1 minus Sn equal to, okay, so terms up to 1 upon n plus 1 are cancelled. So what we get? 1 upon 2n plus 1 plus 1 upon 2n plus 2, 2n plus 2. Also a term, because I am writing here n plus 1 in place of n, so n is replaced by n plus 1, then what we get here? First term n is replaced by n plus 1, then this term will be 1 upon n plus 2, so this term is not here. Okay, because I am writing Sn plus 1, so in every term I am writing n plus 1 in place of n. So if I write in first term n plus 1, then we get n plus 2, then 1 upon n plus 3, and so on. So if I find Sn plus 1 minus Sn, then this is equal to 1 upon 2n plus 1 plus 1 upon 2n plus 2 and minus this term 1 upon n plus 1, which is equal to if I take LCM 2n plus 1, 2n plus 2, n plus 1. Okay, so on simplification we get here 2n plus 1 into n plus 1 plus 2n plus 2 into n plus 1, here 2n plus 1 into n plus 1 and minus here I get 2n plus 1 into 2n plus 2, and on simplifying this, what I get, there will be 1 upon 2 into n plus 1 into 2n plus 1. Okay, so you can simplify these terms, we get this, and this term is what? Greater than 0 for each natural number. Okay, if this term is greater than 0 and this is equal to what? Sn plus 1 minus Sn. So what we find implies Sn plus 1 is greater than Sn for each n, and this implies sequence Sn is strictly increasing sequence. Okay, so we have proved that sequence is increasing sequence. Now we will try to prove that because sequence is increasing, so if its upper bound of sequence exists, then we can say that sequence will be convergent, because we have proved that necessary and sufficient condition for a sequence, for a monotonic sequence to be convergent, is that it is bounded. Okay, and if it is monotonically or strictly increasing sequence and it is bounded above, then it is convergent. So now we will try to find that, because sequence is increasing sequence, so we will try to find its upper bound. So how can find its upper bound? Since Sn equal to 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon n plus n, 1 upon n plus n. We know that n is less than n plus 1, and is less than 1 upon n plus 1. So what we can write? 1 upon n is greater than 1 upon n plus 1. Okay, so every term n plus 1, 1 upon n plus 1 will be less than 1 upon n. Similarly, 1 upon n plus 2 is also less than 1 upon n, and so on. So what we can write? This whole term is less than 1 upon n plus 1 upon n plus up to 1 upon n times, because there are n terms, 1, 2 to n. And if we add, then what we get? This sum is equal to 1, So we find Sn is less than 1 for each n. So every term of sequence is bounded, okay, bounded above by 1. So upper bound exists. Since sequence is monotonically increasing sequence and its upper bound exists, hence sequence is convergent. So we can write, since Sn is monotonically for increasing sequence and upper bound exists, exist, so it is convergent. Hence it is convergent. Next example we are going to solve is if sequence Sn is equal to 1 upon factorial 1 plus 1 upon factorial 2 plus and so on 1 upon factorial n. Okay, we have to prove that this sequence is convergent. So how we can prove? First, write Sn plus 1 equal to 1 upon 1 factorial plus 1 upon factorial 2 plus and so on 1 upon n plus 1 factorial. Okay, n is replaced by n plus 1, and then this term will be 1 upon n factorial. So Sn plus 1 minus Sn is equal to 1 upon factorial n plus 1. This term is always greater than 0. So what we get? Sn plus 1 is greater than Sn for each n. This implies sequence Sn is increasing. Okay, monotonically, or we say strictly increasing sequence. So sequence Sn is increasing sequence. Now we will try to find its upper bound. If upper bound exists, then obviously sequence will be convergent because it is increasing sequence, or monotonically, or we say strictly increasing sequence. Since Sn equal to 1 upon factorial 1 plus 1 upon factorial 2 plus up to 1 upon factorial n factorial. And we know that an important relation, that factorial n, here I am writing factorial n is greater than or equal to 2 raised to the power n minus 1 for each n. So I am trying to use this relation, because if I take 1, then it holds for 2 factorial, and 2 for 3 factorial, this will be 6, and for 3 this will be 4. So factorial n is greater than or equal to 2 raised to the power n minus 1 for each n. And what we can write? 1 upon factorial n is less than or equal to 1 upon 2 raised to the power n minus 1. 1 upon 2 raised to the power n minus 1. So by using this result, what we can write? Sn is less than 1 upon 1 factorial, so I will take n equal to 1, so I get 1, plus 1 upon 2 factorial, so I put here 2, so n equal to 2, then I get 1 by 2, plus 1 by 2 square, plus and so on. Here I get 1 upon 2 raised to power n minus 1. So there are 1, 2 up to n minus 1, these are terms, and one term is this. So total n terms are here, n terms. And this is the geometric progression whose common ratio is 1 by 2. So what we can write? Sn is less than 1 minus 1 by 2 power n upon 1 minus 1 by 2. Okay, so a minus r to the power n upon a minus r. We have used the formula. And this term can be written as equal to, this term is equal to 2 minus 1 upon 2 raised to power n minus 1. Okay, on simplifying we can write this, and this term is always less than 2. So what we get? Sn is less than 2 for each n. hence sequence is bounded above. Sequence is bounded above. Since sequence Sn is increasing and bounded above, so it is convergent. Hence it is convergent. Okay, so if a monotonically or strictly increasing sequence which is bounded above, then it converges to its supremum, so sequence is convergent. Okay, another important example, let an be a sequence defined by a1 equal to 1 and an plus 1 equal to 3 plus 2 into an upon 2 plus an for n greater than equal to 1. Then show that sequence is convergent and find its limit. So we will prove that sequence is either monotonically increasing or decreasing. Okay, we will see here, and if it is monotonical sequence, then we will see that its bounds exist or not. If it is monotonic and bounded, then we can say that it is convergent. Okay, so since a1 is equal to 1, if I find a2 for n equal to 1, so a2 is what? 5 upon 3. If I find a3, then it is 19 upon 11. On solving, that is terms of sequence are increasing. So we can see here a2 is greater than a1 while a3 is greater than a2, and similarly we can see further. So we will prove, suppose that an plus 1 is greater than an. Okay, an plus 1 is greater than an, then we will prove, it is required to prove that an plus 2 is greater than an plus 1. We will prove this. Okay, if I consider the result true for n, then we will prove for next positive integer. So we have considered that an plus 1 is greater than an, then we will prove that an plus 2 is greater than an plus 1. Okay, so I am going to find an plus 2 minus an plus 1. Since an plus 2 minus an plus 1 equal to, so this is 3 into 3 plus 2 an plus 1 upon 2 plus an plus 1 minus 3 plus 2 an, or upon 2 plus an, 2 plus a, which is equal to 2 plus an plus 1 into 2 plus an, 2 plus a. We multiply this term by this and this term by this, and when we solve, we get an plus 1 minus a. But we assumed that an plus 1 is greater than an, hence an plus 1 minus an is greater than 0. So what we get, this whole term is greater than 0. So if we consider that it is true for n and n plus 1, then we have proved for next positive integers. Hence or implies sequence AN is increasing sequence. Okay. Further, since A1 equal to 1, which is less than 2, A2 equal to 5 by 3, which is less than 2, A3 equal to 19 upon 11, which is less than 2, and so on. So we can guess that every term of sequence is going to be bounded above by number 2, and we can prove also. Let if possible, suppose, or we can write, since an plus 1 is equal to 3 plus 2an upon 2 plus an. So what we can write this term? This is equal to 2 minus 1 upon 2 plus an, because 2 into 2 4, and minus 1, this will be 3, and 2a, same term will we get. So 2, some positive number we are subtracting from 2, and this term is less than 2. So an plus 1 is less than 2 for each. That is, sequence is bounded above, implies sequence an is bounded above. Since sequence is increasing sequence and it is bounded above sequence, hence we can write that sequence an is convergent. And if it is convergent, then we can find its limit. So how can we find its limit? Since an plus 1 equal to 3 plus 2an upon 2 plus an. If I take limit n tends to infinity, an is L, which is equal to limit n tends to infinity an plus 1. So I am taking limit of the expression, then what we get? L equal to 3 plus 2 into L upon 2 plus L, or this implies 2L plus L square equals to 3 plus 2L, and we find L square minus 3 equal to 0, implies L equal to plus minus root 3. But sequence, every term of sequence, since first term is 1 and sequence is increasing sequence, so every term of sequence is positive. Every term of sequence is positive. So limit will be also positive, and we take L equal to root 3. Okay, so we have proved here a sequence convergent, and then we have find a limit of the sequence which is equal to root 3. तो फ्रेंड्स, ये लेक्चर्स हमारे आगे भी कंटिन्यू रहेंगे। मोनोटोनिक सीक्वेंसेस पर कुछ एक एग्जाम्पल्स हम अपने नेक्स्ट लेक्चर में भी सॉल्व करेंगे। अगर हमारे वीडियोस आपको पसंद आ रहे हैं तो लाइक करें, कमेंट करें, सब्सक्राइब करना ना भूलें। हमारा यूट्यूब चैनल देखने के लिए आप सभी फ्रेंड्स का धन्यवाद। नमस्कार फ्रेंड्स।